Hi everyone, and welcome to my presentation. My name is George Noarov. I'm a second-year PhD student at Penn, advised by Michael Kearns and Aaron Roth. This paper is joint work with Varun Gupta, Chris Jung, Mallesh and Aaron Roth. Let's jump straight into it. So what is our paper about in a nutshell? We consider an online contextual setting, and we provide in this setting various forms of uncertainty guarantees. We imagine the data points that come to us at each round as being labeled individuals coming from some population. Our uncertainty guarantees then hold conditional on each group in a potentially large and complex collection of subpopulations of this population. Our technique originates from ideas put forth in the 90s by Freudenberg, Levine, and Hart, among others. And it is a simple and general tool that lets us obtain many types of uncertainty estimates in a streamlined fashion. Its main component is the fundamental theorem of game theory known as the minimax theorem. So, first of all, why do we need to care about uncertainty estimation? Up until now, the dominant branch of machine learning research has focused on producing models that are more and more accurate. And we have achieved great successes in this branch. Think neural nets. However, more recently, we're seeing an increased focus on understanding whether or not the model can be made to know when it doesn't know the right answer. In other words, when is the model at its most uncertain over the entire sample space. Such guarantees are very important in practice, and so I guess to give us some visual imagery to feed into our imagination, let's consider a patient and a doctor having a conversation at the doctor's office. And so the doctor is telling the patient that given the patient's features, X, the expected disease severity in 2 days will be F of X. And the patient is rightfully interested in knowing how certain the doctor is of such a diagnosis. The doctor might respond, I have a 95% prediction interval, which tells me that your diagnosis will be between L of X and U of X. However, what does it mean to have this kind of prediction interval? The doctor might clarify that the prediction interval in question is actually a marginal prediction interval. What this means is that the label will fall into this interval 95% of the time if we sample from the entire labeled population. Notice that we won't be conditioning on this current patient's features. Instead, we actually just take the average over the entire population. However, this can be a problematic type of prediction intervals. What can happen, for example, is that the learner, the patient, can be part of a very small subpopulation, which comprises maybe 1% of the entire population. In this case, it would be entirely consistent with this 95% prediction interval guarantee that all of the individuals in this small subpopulations are completely misclassified. So, therefore, the patient decides to dig a little bit deeper into this and asks the doctor to provide more uncertainty estimates that are specific to this patient's features. And the doctor may not have ever encountered any other patient with the same type of features as this patient, of course. But at the same time, this doctor might have seen enough people from some of the subpopulations that this patient belongs to so as to make an informed guess about the confidence of her diagnosis for those subpopulations. And so the doctor might say, well, for African Americans under the age of 50, like you, my 95% prediction interval is A to B. And for women with a family history of diabetes, my prediction interval will be C to D. And for people with egg allergies, my prediction interval will be E to F. That sounds really cool. However, once again, we might run into problems. For instance, depending on our uncertainty estimation procedure, all three intervals might have absolutely no points in common. So even though the patient belongs to each of these three subpopulations in question, but the patient's diagnosis will not be in the intersection of these three intervals. So the difficulties of the type that we've discussed can actually be talked about in a bit more formal of a way. So how strong can our uncertainty guarantees possibly be? Well, ideally, we would like them to be conditional on the patient's features. So if we were to wish for the most ideal predictor ever, we would of course pick the Bayes optimal predictor. We would predict the expectation of the label conditional on this current patient's features. And for our prediction interval, we would of course want its 95% certainty to be as randomized over the labels, conditioned once again on this patient's features. However, these guarantees are pretty much unachievable, especially when feature spaces are rich. For example, if you give me a patient with features X, I've probably never seen such a patient. So I can't judge the uncertainty of my predictions around this patient's point. There's a statistical way out, which is to introduce a parametric assumption and then form uncertainty estimates around the parameters of such an assumption, which will then translate into some uncertainty estimates for our predictions. However, what if we don't want to make such assumptions? Then we might have to resort to a more realistic type of guarantees, such as marginal ones. In this case, we would be averaging over the entire population instead of conditioning on this particular individual's features. So, for example, instead of the Bayes optimal predictor, we would be content with just a calibrated predictor, meaning that we would want our prediction to coincide with the expected true label conditions on that prediction. In terms of prediction intervals, of course, as we just discussed, we would want to have marginal coverage intervals, which means that the 95% probability is over the entire population. There's also another problem that has been thwarting greater and greater uncertainty estimation advances, which is that one often needs to make a lot of distributional assumptions as it appears. For example, in conformal prediction, there's a standard distributional assumption called exchangeability, which roughly means that the future looks like the past. More formally, it means that data points can be swapped without changing the distribution. And this assumption is actually only slightly weaker than IID. So it actually will fail us in many, many real-life scenarios, such as, for example, time series data where there can be correlations between the past and the future, such as covariate shift. Imagine the disease spreading through the population and thereby altering people's features, so altering the demographics. Label shift, so say we've come up with a novel treatment for the disease, and so conditioned on a patient's features, the outcome will now change to being more positive. And various sorts of strategic effects. Consider settings such as lending or hiring, where we might be employing a classifier to decide which applications to select. And unless we frequently retrain our classifier, applicants may definitely consider all sorts of manipulations to their features that would try to game the current deployed version. So there's a lot of instability in the real world, and therefore we may want to try and address that. So our work indeed aims to address these two challenges outlined. First of all, we give stronger than marginal guarantees. Our guarantees are essentially marginal guarantees over groups in potentially a large subset of population groups. So in the special case where the entire population is a single group, we would require standard marginal guarantees. And secondly, we don't make any distributional assumptions. We'll be working in a sequential adversarial setting, and so data could be correlated, could have covariate shift effects, could have label shifts, and could have various sorts of strategic effects. We don't care about that. Our guarantees will hold in all of these settings. So at this point, let me introduce the setting that we'll be working in. We're giving a feature space X, and we are provided with a collection of groups, subspaces of the feature space. This collection of groups can be quite large, and the different groups can overlap in all sorts of complicated ways. Our setting will be sequential. We'll proceed in rounds 1 through some large time horizon, big T. At each round, the adversary first picks a joint distribution over context label pairs, xt, yt, where we assume henceforth the labels to come from the interval 0 to 1. The learner only gets to observe the realized context xt, and the learner does not get to observe the conditional label distribution yt given xt. So think of it as us being able to see the patient and to look into the patient's condition, but not actually being able to see anything further about that patient's diagnosis distribution. So what kind of predictions do we want to make in such a case? Well, for example, we may want to try and predict the mean label, or we may want to predict the mean and the kth moment of the label, such as the variance of the labels. Or we may want to predict at each round a prediction interval around these labels. Finally, having made the prediction, we now get to actually see the realized label for this round. So again, this setting is completely adversarial in that if the adversary wanted to, he could potentially wait until we've submitted our prediction and only then determine the distribution yt given xt. Our plan now will be to jump into our first application, which is on-land multi-calibration in the setting where we're predicting means at each round. We'll define it. We'll then show how to cast the interaction of the learner and the adversary as a repeated game. We'll show that if the learner can perform reasonably well in this game, then we can obtain strong multi-calibration bounds. And finally, we will show how to efficiently compute the learner's optimal strategy at each round of this game, which will give us an implementation of an algorithm that actually achieves these multi-calibration bounds. So once again, we predict the mean mu t at each round. And as customary when talking about calibration, let's partition the learner's strategy space, so to say, 0 to 1, into n sub-intervals, or we call them buckets of equal sizes. Roughly, if mu t belongs to bucket I, that means that mu t is roughly I over n. Regular calibration is a requirement that for each bucket I, the average true label over those rounds when the learner predicted I over n or so should actually also be close to I over n. And a recent add-on to this definition, which has proven to be quite fruitful due to Heber, Johnson, Kim-Rangel, and Roth, is multi-calibration, which requires that we should be calibrated not only over the entire subsequence of rounds, but also over each subsequence corresponding to every group G in a family of population groups. So to define multi-calibration formally, let us consider the following V quantities, indexed by the group, the bucket, and the time point. So for any group G and bucket I, this quantity actually describes the extent to which our predictions mu t were close to the true mean yt over those rounds where, first of all, the patient or the feature vector belongs to group G, and secondly, where our prediction falls into bucket I. And so the requirement of multi-calibration is that all these quantities be small. Formally, we want to ensure that 1 over t times the maximum of the absolute values of these quantities is at most some uniform constant alpha. Then we call our learner alpha n multi-calibrated. So let's think about the structure of this definition. Basically, we're given a bunch of constraints, many of those, and these constraints are linear in the realized labels, y1 through yt. So how do we actually make sure that the target objective is small? There's a bunch of hurdles that we'll need to deal with before we can actually come up with an efficient algorithm. Here they are. First off, our objective is a max of a bunch of things, and analytically speaking, it's non-smooth and so inconvenient to deal with. Secondly, this objective actually takes into account the entire history of the interaction from round 1 through round t, whereas learners' decisions should come at each round, and the learner can't simply wait for any longer. And so the issue here is to try and come up with a decision scheme for the learner that is actually algorithmically tractable. So not overly complicated, such as like taking into account all possible future histories. And finally, the most fundamental change is that at every round, we're aiming to predict the mean of a distribution that we don't know anything about. It's adversarially selected. How do we deal with that? Let's first get rid of the first couple problems here. First off, let's, instead of our original objective, consider a surrogate loss, known as the softmax loss. Instead of the max, we're taking a sum of exponentials with some parameter a that think of it as 1 over root t. The softmax loss actually surprisingly tightly approximates our actual target objective. So henceforth, we'll deal with this loss. And since it's smooth, we can now use the Taylor expansion to bound a quantity that we call delta t. This quantity represents the increase in the loss from round t minus 1 to round t. And so for each round t, we get some bound on this quantity that contains the learner's mu t, the adversary's yt, and in particular, previous round's losses. So let's write this down in a clearer form. Basically, at each round, we can bound the loss increments by this expression where a and b can be essentially treated as constant, which only depend on prior history, but not on what the learner and the adversary will do in the current round. If we can imagine that at all rounds, the learner can get the prediction mu t close to the true label yt, then we can imagine that all these increments will be small. And if the increments are small, then we can bound the overall surrogate loss lt by using a telescoping kind of argument. So now we get to the answer to our second question, how to design a decision scheme for the learner that's not too complicated and that still achieves a small multi-calibration loss. We'll make the learner greedy. Essentially, at round T, the learner will choose MT only with the current round in mind, not caring at all about future rounds. The only objective at round T in selecting new T will be to make the increment delta T as small as possible. So let's focus on round T. And we'll see that the learner-adversary interaction can be naturally thought of as a two-player game, where we are trying to fight over this quantity that bounds this round's loss increments. And the learner wants it to be small, goes first and plays some mu t, potentially a distribution over mu t. And the adversary wants it to be large and goes next and plays the label yt. So it looks like the learner is disadvantaged here because the adversary actually gets to see the learner's action and potentially could best respond to it. But a fundamental fact in game theory tells us that this is not the case. The minimax theorem for two-player zero-sum games asserts that the order of play doesn't actually matter. In fact, even if I go first, I can still find some strategy, the minimax optimal strategy, that will give me the best possible thing I could hope for had I even gone second. So to use this result, we'll need to make the learner's action set finite. This is just a technical restriction. So the learner will play multiples of 1 over Rn for some R. And so by this theorem, despite going first, the learner has this strategy which magically obtains the best possible bound on delta t, even though the learner goes second. And this bound will be as good as if the learner first got to see the adversary's label. But hold on, if the learner knew the adversary's label, then we could just get 1 over 2 Rn close to it by playing the next grid point to the adversary's choice of yt. Therefore, the minimax strategy achieves this even though the learner actually goes first. So now we basically get a guarantee that if the learner plays the minimax optimal strategy, then delta t will be bounded by as small a number as we can possibly do. And so to unwrap this argument, we now plug this bound on delta t back into the bounds on the surrogate loss, and that translates into multi-calibration loss, which gives us our desired existential guarantees. And these look as follows. Basically, we can get a high probability bound as well as an in-expectation bound over the randomness of the entire transcript. Both these bounds essentially say that alpha is at most 1 over root t asymptotically, and the dependence on the number of groups in our family of groups is square root of log of the number of such groups. So first off, of course, we can't improve the dependence on t because even in the simpler distributional setting, it's known that we can beat 1 over root t in terms of calibration. And secondly, we can actually improve our dependence on the number of groups even more. For example, if the patients we've ever encountered between rounds 1 and t are all in at most d groups for some d, so each patient is only a member of at most d groups, then we can actually replace the size of the entire family of these groups with d, which means that we can even get a good finite bound in the case where our feature space is infinite and maybe our family of groups is also infinite. Okay, and now it turns out that there is actually an explicit way for the learner to compute the minimax optimal strategy at each round. In game theory, typically the general recipes to solve a linear program in order to compute such a strategy, but in this case we can actually do an even simpler thing, which is displayed right here. So basically at each round we first compute n quantities, one for each bucket, that essentially represents our performance on that bucket in the past. And this is actually, believe it or not, the bulk of the computational work in this algorithm because we have to sum over the groups that the current patient belongs to. And now that we've computed these quantities, we just look at the 3 possible cases related to these quantities. And in 2 of these cases, we end up predicting with probability 1 1 and 0 respectively. And in the third case, we will cleverly randomize over just 2 of our grid points. So therefore, not only is this algorithm simple, it is also low randomization, which is pretty good. So now that we've taken a look at multi-calibration, we'll briefly mention another application in our paper called prediction interval multivalidity, which is related in many ways to the conformal prediction literature and improves on it in some ways. And we'll briefly define it, then show that deriving existential bounds in this setting is essentially as simple as it is for multi-calibration, and it will display an efficient algorithm that lets the learner compute the optimal strategies at each round. So at each round, we'll now predict an interval, LT-UT. And the bucketing will now work as follows. Your interval is in bucket I, j, if the left endpoint is in bucket I and the right endpoint is in bucket j. Our goal will be as follows. We'll get a constant delta. Think of it as 0.05. And our goal will be to predict an interval such that the probability of the label being in that interval is 1 minus delta. Think of it as 0.95. Moreover, it will require that this holds conditional on each of the population groups in our group family. Similar to multi-calibration, let's consider the following V quantity is now indexed by G, I, and J, where I and J are buckets. For any G, I, and J, such a quantity tells us the following, that we should be close in our coverage interval to 1 minus delta over those rounds where first off the patient or the feature vector belongs to the group G, and secondly our predicted interval belongs to bucket IJ. And now you can possibly already guess the definition of interval multivalidity. It is that 1 over t times the max of the absolute values of these quantities should be uniformly bounded by some constant alpha. And we'll need to make another technical assumption here, which is necessary, that the adversary plays label distributions that don't concentrate overly on any given subinterval of 0, 1. This is just so that we can actually get coverage approximately 1 minus delta. Because if the adversary were to say concentrates the label at 1, then what would happen is that any interval, it's easy to check, would have coverage either 0 or 1, so never 1 minus delta. And how do we derive prediction interval guarantees? We know the drill. First, switch to the softmax loss with respect to these V quantities, then bound the one-step increments of this loss using, once again, Taylor expansions. Next, consider a zero-sum game at each round where the payoff is the obtained bounds on delta t, the increment. Then assume that the learner plays the minimax optimal strategy in such a game, and then get existential bounds from here, once again via telescoping. Why does this work here just as it did in the multi-calibration setting? Well, because suppose we can flip by the minimax theorem the order in which the learner and the adversary goes. So suppose the learner actually knew the adversary's label distribution. Well, we would just look at the density curve for that distribution, and we would read off our 1 minus delta prediction interval quite easily. And so the last goal will be to give an efficient algorithm for finding such a minimax optimal strategy. The existential guarantees, as you can see here, are very similar looking to the multi-calibration ones. And the only question is, how do we actually achieve them algorithmically? The algorithm here is more complicated than it is for multi-calibration. Here we actually follow the already mentioned standard template for solving for minimax optimal strategies using linear programs. In this case, the linear program would even be infinite size due to the adversary's strategy space being all 0, 1, all of the distributions on that. And so our first step is to actually reduce it down to this linear program that you can see here, which is actually exponentially sized. And so for this linear program, we cannot really solve it in polynomial time unless we have a good separation oracle, which we fortunately do. It's based on greedy knapsack packing. And so we use the polynomial time ellipsoid algorithm with this separation oracle to actually find the optimal distribution over intervals for us to play at each round. In conclusion, we've presented a general technique that allows us to obtain stronger than marginal uncertainty guarantees in an online adversarial setting. In particular, our guarantees hold conditional on each group in a potentially large and complicated set of population groups. We provide both high probability and in-expectation guarantees, and besides providing these guarantees, we actually also show how to implement them in polynomial time. In fact, subsequently, we have discovered that this framework can be further generalized to cover convex, concave vector losses in general online environments. You can see the paper at this link. And this more general framework actually allowed us to not only recover multi-calibration prediction rules and other uncertainty guarantees, but also very general no-regret algorithms that in particular encapsulate many known no-regret frameworks such as external, internal, adaptive, etc. And we can also recover Blackwell approachability on polytopes. In the future, there is still a lot of work to be done. First off, we believe our results can be extended without too much hard work along a few practically important directions. First off, from binary, so 0 to 1, we might want to extend this to multi-label settings, as well as maybe extend the prediction intervals guarantees to what's known as prediction sets, a concept being developed in the theory of conformal prediction. Secondly, can the prediction intervals algorithm that we just presented be implemented in a more practical way? Of course, it is polynomial time, since the ellipsoid algorithm is, but the ellipsoid is also very slow. Finally, there is still a lot of work to be done towards the experimental evaluation of our algorithms. And there's lots of interesting questions, such as, for example, whether or not they empirically perform much better or not on distributional rather than worst-case adversarial data. And thank you very much for being with me today. And I wish you a nice rest of your day. Bye.